Hello, my name is Jeff Onko, and this is my end of course project for Duke University Machine Learning Foundations for Project Managers. Okay, so the provided approach and the project goal of this project was basically to be able to model and to use the provided approach that was given to us in the instructions, which was to predict the energy output of a combined cycle power plant. And it used environmental conditions as the features like temperature, pressure, humidity, and vacuum. The first step as given to us was to define the type of task. Since the outcome we're predicting, in this case as given to us, was the energy output in megawatts, that is a continuous number. This is a regression problem, and based off of that. Then it instructed us to choose performance metrics to evaluate the model. The ones that are typically using for this type of model are mean absolute error, root mean squared error, and R squared, which are explained later. Then to go through and identify the input features, and as I mentioned earlier, in the provided data set, those were the 4 sensor readings. Now, to avoid data leakage, the approach was that, and that was taught in class, was the data must be split into 3 parts: training data, validation data, and the final test data. So those 3 types of data sets. Training is obviously where the model learns, validation is used to compare, and then the final test set is held back to evaluate the best model at the very end. And then as a part of the project, the final requirement was us to compare at least 2 different models. I, however, chose to adapt the approach. In order for me to really get into the details of how the data works, how it's related to each other, how the modeling specifically works, and just to get general better understanding of the project itself and this particular part of the course, the things that we learned. Instead of modeling power plant energy output, I wanted to use something that I'm very familiar with and processes that I'm very familiar with. And I decided to attempt to use the model to try to solve a problem I've seen repeatedly over 20 years of software delivery and project manage it. Basically, predicting delays in projects and what caused them and what has the most impact, really. So I decided, as I mentioned, I'm going to try to predict the number of days a project might be delayed. And since that is a continuous value as well, it's also a regression problem, just like the original assignment. So it lined up quite nicely. The 3 performance metrics of the ones I mentioned earlier that I picked was MAE, which basically tells me on average how many days my predictions are off with my model, or MSE, which kind of punishes the bigger mistakes more heavily, and then R squared, which basically shows me how much of the variation in my model explains it from the data, and it's included. The features I included reflect common risk factors that's experienced on the job, team experience, project complexity, resource availability, stakeholder engagement, and dependencies, and there is actually several more, but those are the ones that I chose to use as a part of the features of the model. And in accordance with the instructions, I also split the data into this 3 sets: 65% training, 20% validation, and 15% final. And then I came up with a way to compare 2 different models. The first model that I used, I wanted to represent low, medium, high for all of those types of features. But I used a 1 through 3 encoding, 1, 2, and 3, low being 1, high being 3. In the second model, I wanted to try to capture more of the differences between, for example, a small SaaS integration project and a full ERP implementation like NetSuite or Salesforce. Because the difference between those types of work is quite large. So I wanted a more detailed prediction. That was my goal. And you'd be able to see the difference between the smaller projects and the impact of the larger projects and team experience and so forth. So that was what I was going into this thinking, hopefully my theory, and attempting to prove out. Okay, so for the baseline, as I mentioned in the 1 through 3 encoding, as you can see on the results there with the coefficients, the t-stat and the p-value, as you just go down the line there for team experience, project complexity, resource availability, and so forth, team experience matters. Moving from low to medium and medium to high, it reduces project delays by about 4 days each step. Complexity is the biggest driver. That adds almost 8 extra days of delay. Dependencies are also huge. Resources and stakeholder engagement help. Better resources availability cuts it about 3 days. And if you got people in terms of your stakeholders really involved in your project, as we all know, then that's a positive thing. So that actually cuts about 2.5 days of delay. So as you can see with the p-value there, all being pretty much close to 0, all of these features are very significant. Of the group, as I mentioned, stakeholder engagement is the least influential, but even so, it's still quite large, and the number is still quite large. So basically, this regression confirmed what many project managers already know. Project complexity is really the biggest driver of delay, adding almost 8 days for each level, which makes sense if you think about an ERP rollout, as I mentioned earlier, like NetSuite or Salesforce. There's dozens of interconnected processes versus something way more lightweight, like a SaaS integration, where you're just connecting to an API in a database, etc. On the other hand, experienced teams, better resources, they all play a role, which also matches what I've seen in my work. So good results of that model. Okay, so now for the 1 through 10 encoding, if you remember, I was hoping to actually show the variables in a more accurate way to the actual size of the project or the level of team experience, and see how the model handled that and see what the predictability, if it was more accurate. I basically used the same 3 performance metrics, of course, to evaluate the model: MAE, RMSE, R squared. Same features as before. And also split the data into the same 3 sets. So in order to capture this more fine-grained variation and show those differences between a small SaaS integration and full ERP rollout, this really allowed me to directly compare the two. However, as you see there in the comparison and the findings, the coefficients shrank in size quite a bit. The total effect stayed the same. So for example, in the 1 through 3 model, the complexity had a coefficient of about 8 days or 7.9. going from low to high added around 16 extra days of delay. In the 1 through 10 model, the coefficient was only about 1.8 per step, or almost 2. But across 9 steps, right, that still added up to the same 16 days. So basically, the same impact, which is surprising. So directionally, both models told the same story. The same features were exact matches that had the same impact, team experience, resource availability, and stakeholder engagement. They reduced the delays while project complexity and dependency increased those delays, same in both models. What really came as a shock was a difference in performance. On the validation set, using the 1 through 10 encoding, it did much worse. The MAE and RMSE, as you can see, jumped quite significantly. The average error was about 12 days compared to only about 4 days in the 1 through 3 encoding model. Why? I'm not 100% sure. I'm thinking maybe because 1, 2, 3 is very evenly spaced. In my attempt to show the bigger gap or the more effort involved in team experience or complexity, maybe going from 1, 2, 3, 1, 5, and 10, it wasn't quite as evenly spaced. The distorted set sizes kind of made the model struggle a little bit. I'm not sure, but it's a good thing to see and a good discussion to have about that. But it seemed like it made the model struggle a little bit. In contrast, the 1 through 3 encoding really kept the steps even for the model, and the model performed way better, as you can see here on the results. And one of the ways that we can see this, if you're looking, you can see the R squared close to almost 99% on the validation test set, which realistically is just too perfect, and that was very misleading. So the high MAE showed in practice it wasn't actually accurate. So the final takeaway of the comparison between the two is that the 1 through 3 model generalized better and became my final choice. So then it gave me the results that you see there on the remaining 15% of the data for the final test, which was pretty close to the originals that I did as well on that baseline model for the 1 through 3. It was really the most consistent and realistic results. So that was the best model at the end of the day. But question is this really the best model to answer this question that I was trying to answer? And with the features that I was trying to show, maybe weights would be a different type of model where we're able to use weights might be a better approach. This is linear regression, or multi-class linear regression. The strength of this is that it's super interpretable, which is what I was hoping to get out of it, not only from the model, but from the data that I used and the features that I used, as I mentioned earlier, by using my real world example at work. But that kind of clarity is something stakeholders really appreciate and that I appreciated for me to learn for this course. The weakness, though, is that it assumes a straight line relationship. And if the real world example like this one isn't quite as linear, it can have an exponential impact, I think. So maybe something else, another type of model in another one of the tools that was mentioned for the course might have been a better approach. However, I'm not as familiar with those tools. So I chose this Excel, the first option, because that was the one that I was the most comfortable with. But, random forest, decision tree, softmax, multi-class, where we have the weights. I wonder if using one of those in a different tool might have led to a significant accuracy boost. I know the trade-off is that they're less interpretable, But again, my hope was to get a strong predictive performance out of the model. So maybe one of those might have given a better number or a stronger performance or a good number on predicting that. So I don't know. It'd be a good question to maybe try later in the course, I hope, so that I can learn a little bit more. All right. Well, thank you for your time.